In a hydrogen atom, according to Bohmian mechanics, the electron in the ground state, I repeat, is stationary. And it's kind of a novel result, isn't it? Like in regular quantum mechanics, Copenhagen interpretation, electron doesn't even have a position in the first place in a hydrogen atom. Bohmian mechanics says that it's actually stationary. It does have a definite position and it's not moving anywhere from it. Greetings, this is Eugene the Philosopher, the greatest living philosopher after the unfortunate passing of Quentin Robert D. Nameland, who has been the greatest living philosopher before me. This video is going to be about Bohmian mechanics, which is, if you ask me, a better version of quantum mechanics. So I know how much some of you at least enjoy having some talking points, to share on Facebook or Twitter or anywhere else, even if you're not asked to, okay? So now you have one extra talking point to share with other people. So whenever somebody talks about quantum mechanics, etc., you just say, Bohmian mechanics is so much better, and you link them this video in the comments, in their comments, wherever you're writing this. So that would be very much appreciated, let's put it this way. And, well, I guess let's start. Okay, let's begin. So, let's start with trying to understand what is Bohmian mechanics in the first place. So, as you may know, actually I do recommend my lecture on quantum mechanics, this one, where I describe like the theory in general. Somehow I've lost the presentation itself. I only have like a truncated part where not everything is translated, as you can see. But regardless, so Bohmian mechanics, as you may remember, in quantum mechanics, what was one of the main issues is that we don't really know what reality is, right? Is it particles or waves in particular? Like, what is an electron? Is it a particle in a wave, or a wave rather? And it turns out it's kind of both, right? Wait, where do I have it? Yeah. So, electron, is it a particle or a wave? So, Bohmian mechanics directly introduces a statement that there is a wave that governs the behavior of electron, but the electron itself is a particle. So in a way, we introduce the dualism directly by hand. So we're saying the electron is not a particle and a wave. The electron is a particle, but there is a wave which guides the behavior of the electron, guides the motion of the electron. That's why this theory, Bohmian mechanics, is sometimes called pilot wave theory, where this wave, the pilot wave, is something that creates a landscape, if you wish, for electron as a particle to move in. It creates like mountains and valleys, and electron like flows in these valleys and avoids the mountains, something like that. For example, let me give you this is a book about Bohmian mechanics that I've read a few months ago. It's a pretty good book, so I would recommend it. If you don't want to read it, by the way, there is on Thunderbolt's forum, there is my synopsis, basically my notes that I took while reading. So I'll link it in the description, obviously, so you wouldn't have to read the whole book if you wish to know about it some more. But regardless, returning to the point I wanted to make, like the double slit experiment, because they have a graph which shows these like peaks and valleys really well. There you go. So double slit experiment, we shoot particles from somewhere out there. They fall into one of these two slits, and then we see an interference pattern, right? So this is what the solution of Schrodinger's equation looks like. So this is the landscape. Imagine this is like a topographical map of some terrain. So you have like various heights. These lines represent various heights. So you have peaks and troughs, like valleys and mountains, valleys and hills, or whatever. So this is the landscape created by the pilot wave, by the wave function, and the electron moves in this landscape. Also, we'll touch on this later, but there's a curious conclusion from Bohmian mechanics specifically, applied to double slit experiment, is that if the electron passed through one of the slits, it cannot, you see, trajectories cannot cross this axis, so it cannot go into this area ever. This follows from the solutions of Schrodinger's equation. So let us return to the main point. What is Bohmian mechanics? So we kind of separate quantum mechanics into two areas, which are very different. One area is the wave function, which is governed by the Schrodinger's equation, and it creates this landscape. And another area is particles, and these particles move in this landscape, okay? And this solves, it's an absolutely, as I would say, natural extension of quantum mechanics. It's not an interpretation, as people sometimes say, because, well, I mean, to a degree, you may call it interpretation, but it's an absolutely natural extension of quantum mechanics itself. Like, it's a step that wasn't taken by, like, you know, the founding fathers, so to speak, of quantum mechanics, but it should have been taken. And then so much, like, so much stuff would be explained so easily. Actually, all the paradoxes, all the BS you have in regular quantum mechanics, like all the interpretations, including the complete degenerate, stupid ideas like many worlds interpretations, etc., the like complete nonsensical explanations like Copenhagen interpretation, they would not exist anymore. You know, you wouldn't need any interpretations if you just make this simple step. You say, you know, a particle moves in the landscape created by the wave function, period. It solves everything, like I promise. Like all the paradoxes are solved. And like an extra bonus, like some of the features of regular quantum mechanics which are introduced into it as axioms become conclusions from this principle, from this basic separation. For example, Heisenberg's uncertainty is like a theorem in Bohmian mechanics, and like you can just show that it is the case that it happens. Whereas in regular quantum mechanics, Heisenberg's uncertainty is just an axiom. You just introduce it by hand. Here you can derive it, you know, from the first principles, from this basic separation into a wave and a particle moving on top of this wave, if you wish. Or rather the landscape created by the interference of whatever of these waves. Okay, so yeah, it's a really powerful theory, if you ask me. Some of the conclusions that follow from it, the landscape that this wave function creates, it's actually non-local, which means it depends on the positions of all the particles, okay? However far away from each other they are. So it introduces an intrinsic non-locality into the theory. Basically, it states that the electron in my experiment will move in such a way as if it was aware of the electrons in Andromeda galaxy, like immediately right now, because they also shape. I mean, I'm exaggerating, obviously, but, you know, fundamentally this is the case, okay? So it removes this locality from physics, and many people don't like this. But the experiments show this is the case. Physics is non-local. Like, I'm sorry. If you're a fan of Einstein, like, well, good for you, but it contradicts the experiments directly. Like, our experiments show that quantum mechanics is correct, and as such, Bohmian mechanics is correct as well. All the conclusions from basic quantum mechanics may be arrived at in Bohmian mechanics too. So it has no, you know, no contradictions with regular quantum mechanics. So it's just as good. But I would claim it's much better exactly because it doesn't have the regular paradoxes. It doesn't have like ad hoc things like Heisenberg's uncertainty, or rather, it does have it, but it's not ad hoc anymore. Like, it can be derived from first principles, and it's kind of big. One interesting conclusion from Bohmian mechanics, which you don't have in quantum mechanics. By the way, like, if it's not obvious yet, particles do have precisely defined positions in Bohmian mechanics. It's just that we don't know, or we may not know these positions before we make the experiment, all right? So in regular quantum mechanics, for example, in Copenhagen interpretation, the particle doesn't even have a position in the first place. So, you know, like before you make an experiment or whatever. In Bohmian mechanics, the particle does have a position. It's just that we don't know it, perhaps, right? And this position is obviously determined by the wave that shapes the particle's trajectory in the first place. But the particle can be anywhere in this landscape created by this pilot wave. the wave function. And by the way, there is also, like I didn't mention it, but there is also a so-called quantum equilibrium principle, I guess you can call it, where Bohmian mechanics actually intersects with like statistical mechanics and thermodynamics to a degree, where we claim in Bohmian mechanics that particles are gonna move in the most likely way, the most typical scenario. So if you have such a valley, the particle is more likely to be found at the bottom, right, than at the edges of this valley, right, because it's kind of oversimplifying things, is kind of attracted to this valley, but it's obviously a very abstract notion in the first place, so don't take it too seriously. Anyways, there is this quantum equilibrium hypothesis, which says that some states are more typical than others. So in some places, the probability of finding a particle is much higher than in others. And this, my friends, naturally introduces the so-called Born's rule. Right? What is Born's rule? Not, don't confuse it with Bohr. Born is a different person. So Born's rule claims that the probability of finding a particle in a certain state corresponds to the square of the absolute value of the wave function. But this is exactly what you get when you look at it in this way, like that the wave just creates a landscape. So some places, if you wish, are more probable for the particle to be in than others. So that's how you arrive at the Born's rule naturally. So in regular quantum mechanics, it's just an ad hoc assumption, the Born's rule. In Bohmian mechanics, it's a natural consequence of the theory. So that's why, like I'm telling you, it's a really great theory. It's a natural extension of quantum mechanics. It has no problems with any experiments that can be explained with quantum mechanics. Plus, it has something on top of it. Like, for example, we know if the particle passed through one of the slits, it cannot go through the other. I mean, it cannot go here. So it's kind of, some additional info that regular quantum mechanics doesn't even have. Even more so, I want to show you something else. If you solve by the way, like, Bohmian mechanics in general has two equations they work with. One is regular Schrodinger's equation. That's how we get the same conclusions as regular quantum mechanics. And another is the so-called guiding equation. It basically shows how particles are guided by this wave. But it's also like there's no contradiction with regular quantum mechanics. But if you apply this thinking to like a ground state of hydrogen atom, where you have a proton and electron orbiting it, and you solve these equations, you arrive at a very interesting conclusion that in a hydrogen atom, according to Bohmian mechanics, the electron in the ground state, I repeat, is stationary. And it's kind of a novel result, isn't it? Like in regular quantum mechanics, Copenhagen interpretation, electron doesn't even have a position in the first place in a hydrogen atom. Bohmian mechanics says that it's actually stationary. It does have a definite position and it's not moving anywhere from it. It might be this position, it might be this, it might be this, it might be this, it might be this. We don't know, right, before we make the measurement. But we know that according to the equations, the electron is stationary. So wherever it is, it's not moving anywhere. Because there's a standing wave, this landscape is a standing wave. So that's why the electron is just sitting in the same spot, roughly speaking. So again, a novel result. Like quantum mechanics cannot even define a position of the electron. Bohmian mechanics can define it, and it actually makes an original statement about it, that it's stationary. So you see, something very fruitful is happening. Something which potentially, might be, I don't know, falsified or verified sometime later. Maybe some effects could be derived from it. I don't know. That's a good point. I mean, not a good point. Good thing to think about, let's put it this way. Now, let's talk about some criticism of Bohmian mechanics. Like, there is a completely ridiculous video by Sabine Hossenfelder, this one. You may watch it, but it's completely stupid. I mean, you may watch it in the sense that we'll at least have someone else talk to you about it, okay? But, like, what's her criticism, like this part specifically, the bad? What is she saying? That, well, Bohmian mechanics is non-local, okay? So, as I've said, this landscape directly depends on the position of all the particles in the universe, roughly speaking, right? And like, it's simultaneous. And she says, well, it's bad because, you know why it's bad? She thinks because you can't build a quantum field theory from it, right? Because quantum field theory is based on the idea of locality, like it's integrated, like relativity is integrated into it, etc., etc. But I'm sorry, Sabine, like if experiments show that physics is non-local and you're building a local theory, maybe your theory is wrong, okay? Like if experiments contradict it. Have you ever thought of like, I mean, it's completely stupid, but yeah, sometimes you encounter such ridiculous claims made by even, in air quotes, well-respected people like her. But whatever. I mean, it's complete dog shit, as you can see. Then sometimes people say, well, isn't it Bohmian mechanics a theory with hidden variables? Isn't the Bell theorem forbids theories with hidden variables? It definitely does, but there's a caveat. Bell's theorem forbids theories with local theories with hidden variables. But we just said that Bohmian mechanics is non-local intrinsically, by design, you might say, because the wave function depends on all the particles. So I'm sorry. By the way, not only Bell's inequalities do not forbid Bohmian mechanics. Bell's inequalities were derived by Bell exactly because he wanted to show that Bohmian mechanics is correct. Like this is the cruel irony of history, right? Like Bell was one of the few supporters of Bohmian mechanics. Look, by the way, this is the article from Stanford Encyclopedia, and it's really good. Like I urge you to read it. It's like surprisingly good on Bohmian mechanics. Like it's pretty good. So a reading for today is this. If you want to know about this book, I have like a short preface here where I describe the main properties of the theory, and this article. Like if you still think there is a valid criticism of Bohmian mechanics, there is none, by the way. But if you still think there is, you may read this. Look, so the proof of von Neumann is foolish. That's Bell's words. The proof of von Neumann about the local hidden variables, etc. So the hidden variables in Bohmian mechanics would be particle positions, by the way. So Bohmian mechanics claims that particles do have definite positions. It's just that we may not know it, the positions. I mean them, I guess. But they are defined. So yeah, they would be the hidden variables, the variables we are not aware of before we make the experiment. So wait, it had something. Bell was the prime proponent, almost the sole proponent of Bohmian mechanics. What an irony, right? And people quote Bell as like an argument against Bohmian mechanics. This is so stupid, but yeah, you get what you get. So let's conclude. In my opinion, Bohmian mechanics is a natural extension of quantum mechanics that basically deals with all the problems of quantum mechanics in the first place. Like you may watch my lecture if you want to know more about the problems of quantum mechanics. Like I specifically said, we have a mathematical formalism, which works really well, right? But we do have big problems ontologically. Like if we can't even define what we're dealing with, it's either waves or particles, like what the hell? No positions are defined, no trajectories could be defined. Like what are we dealing with? Well, Bohmian mechanics actually deals with this problem. So we only arrive at the good stuff. And I'm sorry, like if you can't build a theory on top of a wrong statement, which is that physics is local, it's not. I mean, the experiment shows that it's not. And Bohmian mechanics shows that it's not, because it, surprise, surprise, like it fits the experiments really well. So your quantum field theory is wrong. I'm sorry, but this is not an argument against Bohmian mechanics. It's an argument against quantum field theory. Yeah. So to conclude, this is a cool theory. Please tell everyone. And this point specifically, I want to emphasize. Like, I haven't learned about Bohmian mechanics before I was like, I don't know, a third year of the university or something like that. And we haven't been taught it ever. Like I had to find this book and read it myself. Like, Bohmian mechanics is something which is completely unknown to 99% of physicists. And I wonder, like, if we dedicate at least like 1% of all the resources which is dedicated to the development of regular quantum mechanics to Bohmian mechanics, how much advances would we make? I think a lot. And that's why I say we need more people. And that's why I'm making this video. Please tell everyone else Bohmian mechanics is superior to quantum mechanics. If it contradicts your little petty quantum field theory, I'm sorry, your quantum field theory is wrong. Bohmian mechanics is correct. At least more correct than your quantum field theory, let's put it this way. And so yeah, tell everyone about Bohmian mechanics. Read the book, watch my video, talk to me, ask questions and comments, let's discuss. Like, this is a really fascinating theory, as you can see. Like, it has some original results, doesn't contradict any experiments. And arguably, if you dedicate more resources to its development, perhaps some completely novel phenomena would emerge. But that is for the future to decide. Thank you for watching. The eons are closing. If you wish to support me, please consider joining my Patreon. That is patreon.com/philosopher. See the link in the description. Or if you have a scientific theory of your own and you'd like my help in developing it, please join my alternative science coaching program, also available through Patreon.